Welcome to Learn with Us. This is the 17th lecture of Basic Electronics.
First, we will have a quick review of our previous lecture. In your last lecture, you understood what are bipolar junction transistors, and you also studied about types of bipolar junction transistors and modes of operation of transistors. In your last lecture, you also understood current equations that will be used for analyzing transistor circuits. Now, what are the learning objectives of this lecture? In this lecture, you will solve some examples using all those equations that you have studied in your previous lecture. And in this lecture, you will also understand DC analysis of bipolar junction transistors. Now, look at this example. Consider an NPN transistor where VBE is constant when IC is 1 milliamperes. Now, how you are going to find VBE at IC is equal to 0.1 milliamperes? Okay. For this, we will use our second equation that we have studied in our previous lecture, which is IC is equal to IS e raised to the power VBE divided by NVT. We are taking VBE here because here this transistor is NPN. Now we know that here this VBE is constant. It means its value is 0.7 volts here, and we know that the value of thermal voltage is 25 millivolts, and for suppose this N is 1 here, and we know the value of IC, it means only IS in this equation is unknown. So first we'll find IS, which is saturation current. Now we'll put these values in this equation A, and we get 1 milliamperes is equal to IS e raised to the power 0.7 divided by 1 multiplied by 25 into 10 raised to the power minus 3. If we rearrange this equation, we get IS is equal to 1 into 10 raised to the power minus 3 divided by e raised to the power 28, and after solving this equation you get IS is equal to 6.915 into 10 raised to the power minus 16 amperes. Okay, so this is the value of saturation current here. Now we will find VBE at IC is equal to 0.1 milliamperes. We'll use the same equation. IC is equal to IS e raised to the power VBE divided by NVT. Now we know that this IC is 0.1 milliamperes. The value of IS is this. We know N is 1, and we know what is the value of VT. So after putting all these values in this equation, we get 0.1 into 10 raised to the power minus 3 is equal to 6.915 into 10 raised to the power minus 16 multiplied by VBE divided by 1 multiplied by 25 into 10 raised to the power minus 3. Okay, and if we rearrange this equation, we get 0.1 into 10 raised to the power minus 3 divided by 6.915 into 10 raised to the power minus 16 is equal to EVBE divided by 25 into 10 raised to the power minus 3. Now, in order to remove this exponential term, we'll take natural log on both sides. So, and if we solve this term, we get 1.44 into 10 raised to the power 11, and here we are taking natural log on both sides. So we get this equation. Okay, we know that if we take this natural log, then we get this x in answer. It means now we'll get 25.69 is equal to VBE divided by 25 into 10 raised to the power minus 3. Now if we rearrange this equation, we get VBE is equal to 25.69 multiplied by 25 into 10 raised to the power minus 3, and after solving this we will get VBE is equal to 0.642 volts. So this is the value of VBE at IC is equal to 0.1 milliamperes. Okay. Now look at this example. If you have a PNP transistor where saturation current is 1 into 10 raised to the power minus 11 amperes, beta is 100, collector current is 1.5 amperes, then what is VEB? For this we will use this equation. IC is equal to IS e raised to the power VEB divided by NVT. Here this transistor is PNP, therefore this voltage is VEB here, and this is equation A. We know that here this IC is 1.5 amperes and this IS is 1 into 10 raised to the power minus 11. This VEB is unknown, and again we are taking N1, and we know that VT is 25 millivolts. So we put these values here in this equation, and if we rearrange this equation, we get something like this. We have VEB divided by 25 into 10 raised to the power minus 3, and now this is 1.5 into 10 raised to the power 11 is equal to EVEB divided by 25 into 10 raised to the power minus 3. Now again we'll take natural log on both sides, so we get ln 1.5 into 10 raised to the power 11 is equal to ln EVEB divided by 25 into 10 raised to the power minus 3, and after solving this we get 25.73, and here we have VEB divided by 25 into 10 raised to the power minus 3 If we rearrange this equation, we get VEB is equal to 25.73 multiplied by 25 into 10 raised to the power minus 3, and after solving this you will get VEB is equal to 0.643 volts. Okay, so this is your answer. Okay, now look at this example. If base current is 14.46 microamperes and collector current is 1.46 milliamperes, and you have to find alpha, beta and is here when VBE is constant. So how you are going to find these unknown values? First, we will find collector current IC. From equation 1, we know that IE is equal to IB plus IC. So if we rearrange this equation, we get IC is equal to IE minus IB. Now we'll put values here. We get 1.46 into 10 raised to the power minus 3 minus 14.46 into 10 raised to the power minus 6, and this will give you IC is equal to 1.44 milliamperes. Okay, now how you will find alpha? From equation 3, we know that IC is equal to alpha IE, and it means alpha is equal to IC divided by IE. Here we know that IC is 1.44 into 10 raised to the power minus 3 because it is milli, and IE is equal to 1.46 into 10 raised to the power minus 3. So after solving this, you will get alpha is equal to 0.986. Okay. Now for beta, we will use equation 4, which is IC is equal to beta IB. It means now beta is equal to IC divided by IB. Now we'll put values here in this equation. We get beta is equal to 1.44 into 10 raised to the power minus 3 divided by, this is 14.46 into 10 raised to the power minus 6, and this will give you beta is equal to 99.585. Now for saturation current IS, we'll be using equation 2, which is IC is equal to IS E raised to the power VB E divided by NVT. It means this IS is equal to IC divided by EVBE divided by NVT. Okay, now we'll put values here. We get IS is equal to 1.44 0.44 into 10 raised to the power minus 3 divided by E raised to the power 0.7. We know that this N is 1 and Vt is 25 millivolts. So here we have 1 multiplied by 25 into 10 raised to the power minus 3, and after solving this you will get Is is equal to 1 into 10 raised to the power minus 15 amperes. Okay, so these are your unknown values here. Okay, now we will understand DC analysis of bipolar junction transistors. It helps us to determine all the DC terminal currents, that is base current, collector current and emitter current, and voltages for both N-type and P-type transistors. These voltages are VB, VC and VE. Now look at this circuit. Here we know that this is the direction of emitter current, this is the direction of collector current, and this is the direction of base current. Now here this IB is DC base current, this IE is DC emitter current, this IC is DC collector current, this VBE is DC voltage at base with respect to emitter, this VCB is DC voltage at collector with respect to base, and this VCE is DC voltage at collector with respect to emitter. Here this VBB and this VCC are supply voltages to base and collector. If there is VEE, then it is supply voltage to emitter. Note that this VEE is not equal to VE. Similarly, VBB and VCC are not equal to VB and VC. Why? Because this VEE, VCC and VBB are supply voltages, whereas VE, VC and VB are nodal voltages. Okay, this VC is here, VE is here and VB is here. Okay, these are nodal voltages. So how you are going to start your analysis if you have a circuit like this? If this base emitter junction is forward biased, then it is like a forward biased diode and it has a nominal forward voltage drop of 0.7 volts. It means when this emitter base junction is forward biased, then here this VBE is 0.7 volts. Okay. Now as you can see here, this emitter is at ground. It means it is at 0 volts. And if we apply Kirchhoff's voltage law here in this loop, what would be our KVL equation? If we start from this point, it is minus VBB this terminal of this resistor is positive and this is negative, and the voltage drop across this resistor is VRB. So here we write plus VRB plus VBE is equal to 0, and if we rearrange this equation we get VRB is equal to VBB minus VBE. From Ohm's law we know that V is equal to IR. It means here this VRB is equal to IB RB. So if we put this value of VRB in this equation number 1, we get IB RB is equal to VBB minus VBE. So the base current will be VBB minus VBE divided by RB. So this is the equation of DC base current for this circuit. Okay. Now, if we look at this region and if we apply KVL here from this point to this point, here we have VCE, then what would be our KVL equation? We start from this point, it is minus VCC plus, here this terminal of this resistor is positive and this is negative, and here voltage drop across this resistor is VRC. So we have plus VRC here plus VCE is equal to 0, and if we rearrange this equation we get VCE is equal to VCC minus VRC. Again, from Ohm's law we know that this VRC is equal to IC RC, and if we substitute this value in this equation number 2, we get VCE is equal to VCC minus IC RC, and now if we rearrange this equation we get IC RC is equal to VCC minus VCE. So this IC will be equal to VCC minus VCE divided by RC. So this is the equation of DC collector current for this circuit. Now, how you are going to find the value of emitter current IE? We know that from equation 1, IE is equal to IC plus IB. Now, we have derived the equations for collector current and base current in our previous slides. So, we'll find the values of these currents from those equations, and after finding their values, we put those values here in this equation, and this is how we'll get the value of emitter current. Now, look at this region. If we apply KVL here and if we start from this point, then what would be our KVL equation? It will be minus VCB plus VCE minus VBE is equal to 0. And if we rearrange this equation, we get VCB is equal to VCE minus VBE. So this is the voltage drop across the collector base junction. We know that this collector base junction is reverse biased in active and cutoff modes of operation, whereas it is forward biased in saturation mode. Okay. Now, how you are going to find nodal voltages VE, VB, and VC? Now, if you look at this circuit, we have VC here, VE will be here, and here we'll have VB. As you can see, this VE is connected to ground. It means here it is at 0 volts. It means for this circuit, VE is equal to 0 volts. Now, how you are going to find VB? You apply this formula of current here, which is VBB minus VB divided by RB, because if you look at this region and if you start from this point, then this is higher potential, this is lower potential, and this is resistor. So this is the formula of current here. And from our previous slide, we know that the formula of DC based current is VBB minus VBE divided by RB. So after finding the value of base current from this equation, we put this value here. Now we know the value of VBB and we know what is the value of RB. So this is how you will find this nodal voltage of base, which is VB. Now what about VC? For VC, you'll use this formula VCC minus VC divided by RC. And from our previous slide, we know that DC collector current is equal to VCC minus VCE divided by RC. So after finding the value of collector current from this equation, you put this value here. You know what is the value of VCC and what is the value of RC. So this is how you will find the value of nodal voltage of collector, which is VC. Now look at this example. If you have a circuit like this and if you want to find terminal currents, that is IB, IC and IE, and nodal voltages VB, VC and VE. So how you are going to analyze this circuit? For suppose here the value of beta is 150 and all these terms are unknown. Okay, so how you're going to start your analysis? First, we will find base current IB using formula VBB minus VBE divided by RB. Here, as you can see, VBB is 5 volts and we know that the value of VBE is assumed to be 0.7 volts. It means here we will write 0.7 volts and here this RB is 10 kilo ohms, and after solving this you will get for 30 microamperes, which is base current. Now how you are going to find collector current. For this we will use this formula VCC minus VCE divided by RC. But here we know that this term VCE is unknown. So what we are going to do now, we will use another formula, which is IC is equal to beta IB. Here we know that beta is 150 and IB is 430 microamperes. So after solving this, you will get 64.5 milliamperes. Okay, so this is your collector current. Now we will find emitter current, and we know that the formula of IE is IC plus IB. Here this IC is 64.5 milliampere, and we know that this IB is 430 microampere. So after solving this, you will get IE is equal to 64.9 milliamperes. Okay, now we will find nodal voltage of collector, which is VC. So we use this equation IC is equal to VCC minus VC divided by RC, because we know that here we have VC. Okay, so now we know what is IC. IC is 64.5 milliamperes, and here this RC is 100 ohms, and here we know that this VCC is 10 volts and this is minus VC. Now if we rearrange this equation, we get VC is equal to 10 minus 6.45, and it will give you VC is equal to 3.55 volts. Okay, so this is the value of nodal voltage of collector. Now we will find nodal voltage of base using this formula. IB is equal to VBB minus VB divided by RB, and here this IB is 430 microamperes and this RB is 10 kilo ohms, and this VBB is 5 volts, and here we have VB. Now if we rearrange this equation, we get VB is equal to 5 volts minus 4.3 volts, and it will give you VB is equal to 0.7 volts. Okay, now if we look at this, here we have this VB and here we have VE. Now as you can see, this emitter is at ground. It means here we have 0 volts. It means the nodal voltage of emitter is 0. Okay, now if we look at our answers, VC is greater than VB because this VC was found to be 3.55 volts and this VB is 0.7 volts. It means the collector base junction is reverse biased here. And if you look at another condition here, this VB is greater than VE because this VB is 0.7 volts and VE is 0 volts. It means emitter base junction is forward biased here. And we know that when this emitter base junction is forward biased and this collector base junction is reverse biased, it means the transistor is in active mode. Okay, so these are your answers. Now here is your class task. For this circuit, you have to determine all terminal currents, that is IB, IC and IE, and all nodal voltages, that is VB, VC and VE, and also find the mode of operation of transistor here. It means you have to find whether this transistor is in active mode, saturation mode or cutoff mode. Okay. Now that's all for today. What are the key takeaways of this lecture? In this lecture, you solved some examples using all those equations that you have studied in your previous lecture. And in this lecture, you also understood DC analysis of bipolar junction transistors, in which you studied how you are going to determine terminal currents and nodal voltages.
Thank you for watching this video. If you have any questions, then write your questions in comment section of this video. Don't forget to subscribe our channel and share it with your friends and family. Thank you.